couple things I want to mention. Had a conversation with a student a few days ago, a few class days ago, and they came up to me after class and they said, Ms. Brooks, I would like to improve my grade in this class. And let me kind of show you how they came up to me. They came up to me like this. And they said, Mrs. Brooks, I'd like to improve my grade in this class. I've currently got da-da-da, I'm doing this, this, and this, and this. What can I do to help my grade? Well, as they're talking to me, this is immediately after class, and as they're talking to me, I'm seeing something going on their phone. I couldn't tell what it was, but I realized as I was talking to her, it was a video of some sort. I have no idea what it was, but it was a video on the phone. And I said, get rid of the phone. And she looked at me funny and I said, get rid of your phone. Quit paying as much attention to your phone. You want to know how you can improve your grade? Get rid of the phone. Of course, she probably didn't like that. I said get rid of the phone. But guys, I want to tell you all something. You all are different than I was. I know that. I'm not saying it's a bad thing. But I want to show you, I want to just kind of try to get you to see what I see. Okay? In that little scenario, and I've seen it in this class as well, in that little scenario, this is what happened and what happens. You come to class and you are engaged. Overall, you guys are engaged. There are a few of you who still sneak in the phone time and don't really pay 100% attention, working on something else maybe, but overall, my students are engaged in class, which is great. And you're doing well in chemistry class overall. But here's what's happening. You're engaged for 2 hours and you're totally focused on chemistry. Overall, few goat stories or cows, but overall, you're engaged in chemistry. And then, as soon as you start putting up your notes, this is what you do. No, and you all do it this way. I can't do it like you do it. And you know what? Your brain, as soon as you've gotten that thing in your hands again, you've gone like 10 places. You know what Jimmy's doing tonight, and Mom said do this and that, and oh, I forgot to pay the rent, and oh, blah, 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 and oh, what are we having to eat, and oh, I've got to go to the grocery store, and da-da-da, and your brain just went wacko. That particular student, as soon as that day, this was just one little snippet that I saw. As soon as that student got out of class, they started watching some video. I have no idea what the video was. Might not have been a bad thing. I'm not saying it was bad. But what did they do to their brain? It's like they just whacked out everything they'd spent 2 hours focusing on and went to another realm. Now, am I saying that you should never pick up your phone? No. But if you truly want to do better in a class, then get rid of this thing a little bit. As soon as you get out of class, what have I said? Review your notes. I'm not saying spend 30 minutes or an hour. I'm saying read over your notes and concentrate for a minute. There was a day, and I don't remember what day it was. I don't remember if it was a test day or just a day that I was walking around helping you with some problems you were doing. And I walked around and I saw phones that were flipped up, which personally I would recommend you not keep your phone flipped up where you see the face of it. I'd recommend you keep it flipped over. But I saw some phones flipped up. And as I was walking around, like I said, it might have been the test, I don't remember. But I see the screen of these phones and they're covered with notifications. And you all know some of you are like that. As soon as you get out of class, you've got 15 things you've missed. Guys, you're living in a different world. And I know that you all think I can handle it all. But if you want to handle it better, why don't you put it away? Get off Facebook, get off Twitter, get off all that junk. Tell people, you know what, if you want to talk to me, call me up. It's called communication. Try it. Now, if you don't care about improving your grade and you are happy as a lark, just shut up, Miss Brooks, leave me alone. I'm fine and dandy like I am. But there have been two people, one sent me an email and one came to me, and that's the story I described to you, and have said, and these weren't even bad grades, these were C's wanting B's. Put your phone away. Try it and see if it helps, okay? One last thing, because I know sometimes it's frustrating when somebody tells you stuff like this, and maybe your parents, and I'll be honest with you, I get mad at my younger brother. I started saying my little brother, but he's a lot bigger than I am. But he's my younger brother. He has 3 little boys, 7, 5, or 8, 6, and almost 4. And the 8-year-old already has an old phone somebody else gave him, and he plays games on it. When he has not got his phone, he and I are best buddies. When he has access to that phone, he is a different kid. Well, my brother fusses at him about this phone. Guess what my brother has in his hand all the time? The phone. Some of your parents probably fuss at you about your phone usage, and then what are they doing all the time? They're on their phone. You may not have the relationship you can fuss at your parents, but just so you know, I do have a Facebook account, but you can go maybe find me, I don't know. I hope if you do find me, you don't find any pictures though, because I don't post anything on it. I have a Facebook account basically because I was told to get a Facebook account for our business, and then I never update it, so it's not worth 10 cents. But occasionally when I do get on Facebook, honestly, it usually leaves me feeling like crud. Because when I get on there, I'll spend 30 minutes wasted time I could never get back. And what I found out when I go on Facebook are things that make me mad I didn't know about them ahead of time. Like when I was, I don't know, a few years ago, I found out my best friend from high school, or all the way through school, her daughter, one of her daughters got married, the other one had a baby. Well, why wasn't I invited to the wedding, you know? And then you find out, well, so-and-so's husband just loves them so much, and they gave them all these beautiful flowers, and their kids are just perfect. And look at this family photo they had that got on Facebook. And you know what? Who cares? Why don't I post my husband's a jerk, and I can't stand life? You know? I mean, that's what you don't see on Facebook. But it's all real. No, my husband isn't always a jerk. He's a nice guy. But all of that, do you see? So I am trying to tell you things that I'm not like doing the same thing you're doing, because I honestly don't. And my kids, my 14-year-old, thankfully, doesn't care anything about a phone. She thinks it's just stupid. I'm very fortunate in that. Now my 11-year-old's the one I'm going to have to worry about. She's the one who wants to play games on it, or she's on YouTube videos. You know, it may be Barbie at this point, but in the future it's going to be something different. So I have to like really nip her in the bud. So it's hard, guys. It can be addictive. I know. On my day off, you know, I told you don't watch TV, rest. We're going to be building a metal building. I probably spent 30 minutes on the computer or the iPad looking at pictures of metal buildings and like Pinterest and stuff. Oh my gosh, you can sit there for 30 minutes and see the same thing 50 times, and you still can't find the one you found 5 minutes ago that you wanted to print out, but you waste, I mean, oh my goodness. And finally I was like, this is wasting my time. I need my day off. I don't need to look at these. So I just like, I had to go. So I understand, okay? I understand. But please try it. If you want to improve your grade, try it. Maybe even improve your life. Try it. Okay? Just my sermon for the night. I won't give you more. You got a calculator? All right. All of these problems, honestly, I probably could have just said, do these problems, because it's pretty much self-explanatory. Mathematical formulas for concentration. That's what we're doing. Mathematical formulas for concentration. So if you look through here, we are going to be calculating concentration of solutions. That's where we were before we left. We've talked about solutions. We're going to be measuring concentration in weight volume percent. So this is a mathematical equation you need to know. Volume percent. We also are going to be doing parts per million and molarity, which those are on the other page. So let's just simply run through these and get going. It says chloroseptic sore throat spray contains 0.35 grams of the phenol dissolved in 25 milliliters of solution. What is the weight volume percent concentration? Guys, these are simple plug and chug. So weight volume percent equals, what's my mass? 0.35 grams over what? 25 milliliters times 100. Plug it all in and tell me what you get. Tell me again, I don't have it in front of me. 1.4%, that's right. Now, one of my frustrations with the medical field is that they list concentrations in percentages, but they don't tell you if it's weight volume or if it's volume. And that's hard to me because I don't know what they're talking about. So after lots of time, I have finally figured out most of your medical concentrations are going to be weight volume unless it is an alcohol. That's general rule of thumb. The other rule of thumb is if the solution was made with a solid dissolved in a liquid, like salt dissolved in water, then it will be weight volume. But if it's a liquid in a liquid, it will be volume. And that's where your alcohols are volume, because it's a liquid in a liquid. Now, most of the time, though, you're not going to know was it a solid dissolved in a liquid. You won't know that. But most of your medical concentrations are going to be weight volume. Do the next one. And there's one thing you need to fix on that one before you get started. Did everybody sign in? Okay. What do you need to fix on this before you get started? Milligrams to grams. So somewhere do milligrams to grams. And you can do that in your head, and that's great if you can. And then just simply plug and chug. What do you get? 0.5%. So 0.5, and the way you write it is actually 0.50% weight volume. I like to put weight volume just so everyone knows how we did it. Any questions? I mean, I think most of you, that's pretty easy. That's not going to be something really hard for you to do. What is this useful for? Lots of things. And let me show you what I think is one of the most useful capabilities of percentages. First of all, what is percent? What's another way we could say percent? It's parts per 100. Do you agree? It's parts per 100. Well, this means 1.4 grams per 100 milliliters. So if I said to you, we have a 1% weight volume phenol solution, that means there are 1.4 grams of phenol in 100 milliliters of the, and I'm not writing all the words, sore throat spray. Does that make sense? Now let's throw another scenario in here. Child finds the bottle, 1-year-old, finds the bottle of chloroseptic sore throat spray, gets it open. It's nice and pretty. They drink it. Whole bottle. What will someone figure out? What's important about that scenario? Oh, great, kid won't have a sore throat for a year. Is that what you're thinking? I'm like shocked that you're not getting what we're saying here. What are you going to call first? Not Ghostbusters. What are you going to call? Poison Control Center. First of all, you're going to call Poison Control Center. You're going to have an idea about how much they drank. If the bottle was full, you'd say they drank and read the bottle, however much was in the bottle. What is someone on their end probably going to calculate? How much phenol they actually consumed. You follow? So if they know the percent, are they going to be able to figure that out? Yeah. So little Jimmy swallowed, whatever, 2.4 grams of phenol, whatever. Well, the lethal dose is 3 grams. You might want to go get his stomach pumped.
Is that like on when it says like active ingredients and it says
yes,
acetaminophen,
yes. And it will usually say, it won't necessarily say percentages though. A lot of the medicines aren't necessarily listed as percentages, but they may say, and that's this Cydectin. This is a true medication for cattle and goats, etc. It is listed this way. And so you can calculate the percentage. So in this case, for instance, right here, we did the percentage is 0.5% weight volume. So what does that mean? 0.50 what? Grams per 100 milliliters. That's what that means. So it's 0.5 grams of the moxidectin per 100 milliliters of the solution. But yes, that is what that means. So, and I don't have any of those bottles with me today, but like if you look at any cold medicine, it will say the active ingredients and it'll give you the number of grams, and it's usually per 5 milliliters or 10 milliliters, depending on the cold medicines. I know that. So guaifenesin or it's not Sudafed anymore, but I can't think what it's called. But yes, that's what you're talking about. That's exactly what we're talking about. Okay? Alcohols. Or actually, let me go backwards. I didn't say this, but you might know me well enough to know the answer. What could these be used for? Say it again. Dimensional analysis conversion factors. Does that make sense where we're going? So like if we knew on that kid's sore throat spray, if we knew they drank a Coke can full of it, and that's 255 milliliters, then could you do 255 milliliters, set this up, and convert that to grams of phenol? Follow? That's what you're going to be doing. Okay? Volume, or alcohols. Most of your alcohols are going to be in volume. Where do you see rubbing alcohol? Or where have you seen rubbing alcohol before? Anywhere, I don't care. There's tons of places you've seen it, but give me an example. Doctor's offices, you see it. It's in the strips or the pieces of gauze that they rub your arm with before they give you a shot. You can go to Walmart and just look at the alcohols, the rubbing alcohol in the medical section, and you'll see a 70% rubbing alcohol. You'll see I think there's a 90%. That means 70 milliliters of the alcohol, which is the isopropyl, in 100 milliliters of total solution, and part of that's water. So it's not a straight up alcohol. Okay? The 90% I think is the most you can get of the isopropyl. So here we're doing what is the volume percent concentration. So volume percent is, what do we put on top? Ethanol or the wine? Ethanol. So it's 101 milliliters over 750 milliliters times 100. And what do you get? So 13.5% volume. Again, which means what?
13.5%.
No, 13.5 milliliters of the actual ethanol in 100 milliliters of wine. That's what that means. For every 100 milliliters of wine you consume, you are getting 13.4 or 13.5 milliliters of ethanol. I don't drink. What does wine come in? Half-liter bottles? I don't know. What liter bottles? What's it come in? It does come in 750 milliliter bottles? Okay. Okay. So in a and so basically they've already done the opposite of this. They've already told you 101 milliliters of ethanol in the 700, so in the entire bottle. So if you drink the whole bottle, that's how many milliliters of ethanol you get. Okay? All right, and the next page tells you exactly what I just said. Percent concentrations can be used as conversion factors, or the information could be used. So we have our cow. She's a parasitic cow. That means she has worms. Worms live in the animal's stomach and basically eat off the animal's blood supply, which then can lower the blood of the cow. Goats are the ones who have more problems with parasites than cattle, but you have parasites in cattle as well. And it says Cydectin is a pour-on wormer. I'm going to go medical route for just a minute here. Are there medications in human medications that are absorbed through the skin? Yes. Does anybody know some that are? Say it again. Different creams, so like hydrocortisone cream if you've got eczema, or different steroid creams if you've got eczema. What about the sex hormones that are used for hormone replacement therapy? Some of those, estrogen patches, have you ever heard of those? I know you don't wear those, neither do I, yet. No. But you know what I'm talking about? You've heard of those? So the patches or creams that they could use, okay? Nicotine patches, that's not a hormone, but is that a drug that's absorbed through the skin? So is this totally crazy that you can pour a medicine on a cow and it would get absorbed in their skin? Not really, but it is kind of, if you think about it. What's leather? Cowhide. Isn't that wild? Think about that for a minute. Leather, imagine if you will, this is a corny scenario here, but put your leather coat on and lean over and you're the cow now, right? Okay? And so along your back, I'm pouring the Cydectin. This is exactly what I do. So cows on all four legs, or bull, on all four legs, and leather coat on, and you're pouring the Cydectin down their back. And it takes care of the worms in their gut. That's cool, isn't it? It's pretty. It works that way. That's really how it works. So it's pretty neat. So, and for the recommended dose is 0.5 milligrams per kilogram of body weight. That is a form of concentration, except that it is mass this time. Mass of drug per mass of body weight. And then the other concentration is each milliliter of drug contains 5 milligrams of moxidectin. So the first is the dose that the animal should receive. The second is how the drug is distributed. What are each of these? What are they going to be used for in my problem? Conversion factors. So this is a conversion factor, and this is a conversion factor. Which means what's my given? 1,400 pounds. This is a big cow. So 1,400 pound cow. Now guys, I want to warn you when you get started on this. What do you have to get the cow's mass into? Ultimately what? Kilograms. Why? Because then you'll know how much drug per kilogram of body weight. Don't get confused and think you need to go to milligrams with this 1,400 pounds. You need to take 1,400 pounds to kilograms, then use this. Do it. Do this problem. Couple ways you could do this. If you know the fast way to convert pounds to kilograms, you could do that. I'm going to do the 454 grams in a pound. Again, there's other ways you could do this. I would make a note that this all is body weight. All of that's dealing with body weight. Then what do we do? 0.5 milligrams of drug per 1 kilogram of body weight. Now we're out of body weight into drug. Does that make sense? Now what? 1 milliliter is what? 5 milligrams. Milligrams cancel, and my final answer is what? How many? 64. Should be, actually, you know what? It should be 60. I think in my notes on the other day I did this in my original notes. Make that 0.50 so we can do the 2. I apologize. But you are correct if you put 60. But put the 0 up there. Either way, you've got the gist of it. And again, you were correct in 60. I wanted 2 significant digits, so I added the 0. The next problem deals with using weight volume percentage as a conversion factor. So what I'm going to do with this problem is I'm going to remember that this can be a conversion factor, and what can I call this? 5 what? Per 100 milliliters. So that means it's 5 grams of the ketamine in 100 milliliters of the solution. So that is a conversion factor now. What's my given going to be? 75 milligrams. So start with your 75 milligrams now and go. And what do you get for your final answer? 1.5 milliliters. Yes or no? Anybody else get that? All right, do the last one. You do the last one. What do you get? 2.3 grams? Yes or no? What is that? 2.3 grams of what? Sodium chloride. Good, you got it. I would encourage you to redo these because it makes sense now, but what I've tried to stress to you is how that percentage converts to a conversion factor. But I'm afraid you'll forget it if you don't do more of it. So I hope you'll take the time to do more of it. Parts per million is the same process because if you recall, I just said that percentage could be parts per 100. So parts per million is the same thing, except this time we're going to be multiplying it by 1 million. Have you ever heard of parts per billion? Or parts per thousand. All of these are methods of measuring concentration in very small quantities. All of these work on the same principle. The difference in what we're doing with parts per million is that the unit type is the same, meaning this is mass over mass, this is volume over volume. We don't have a parts per million or a parts per billion that's a mass volume. They're either mass mass or volume volume. And as long as the units are the same, then it works. You don't have to have them in grams, they can be in kilograms, they can be whatever, as long as they're the same. Because it's the mass over the mass, the volume over the volume. Question, so again, add this to your list of need to know. Add that to your list of need to know, the formulas. And it says, what is the concentration in parts per million of DDT in the tissues of a seabird that contains 50 milligrams of DDT in 1900 grams of tissue? So in this case, we actually have the DDT listed in grams, or milligrams rather, and we've got the body tissue of the bird in grams. What do we have to do? Get them both in the same unit. It doesn't matter what the unit is, just get them both in the same unit. What do you want to do? Put them in what? Okay? So get them in grams. So you get 0.050 grams of DDT. What is that in our formula? Is that the solute or the solvent or the solution? That's the solute. What's the solution mass? 1900 grams, good. And this time we're multiplying it by 1 million. What do you get? Come on. What do you get for your answer? 26. 26 parts per million. What does this mean? This means that there are 26 grams in 1 million grams, or it could be 26 milligrams in 1 million milligrams. You see what we're doing? If you had 1 million balls, how many of them would be red if they were 26 parts per million red? Does that make sense? That's what we're talking about. Now, let's talk real quickly about DDT. Anybody know what it is? What it was used for? Pesticide. Do you by chance know the name of the book that made its use famously banned? You know anything about it?
I know what you're talking about with the lady, she found out with eggs, but I just can't remember the name.
You're one of the few students who knows that. Good. Good for you. Rachel Carson wrote a book called Silent Spring. And this was she wrote this, I believe, in the 50s or 60s, probably the 60s, I think. And DDT used to be, you know how the malaria outbreak in Miami and down in Florida, wasn't it malaria? No, it wasn't. It was Zika virus, not malaria. Zika virus. You remember the Zika virus outbreak this summer, and they were spraying the mass spraying for the mosquitoes? DDT used to be used in mass spraying like that. And what Rachel Carson started seeing is she was seeing that, yes, the insects were dying, but there were fewer birds. And then why were there fewer birds? Well, what happened was the birds would eat the insects that had been exposed to the DDT, maybe, I'm assuming, before they died, because most of the birds would eat them alive, not dead. And so they were getting these insects after they had been sprayed, and then the DDT, I believe, was causing the birds' eggs shells to be weak. You remember this part or not?
Yeah, they were causing the shells to be soft.
And so there were fewer birds being born or hatched, you follow? And so why was the name of her book Silent Spring? If all the birds quit singing, it would be a silent spring. So it's a pretty interesting book. It is an interesting book, but it was using literature to help stop the massive spreading of the DDT, and it did. It got stopped. It's not used anymore. So it's a pretty interesting book to read. Molarity is the last concentration calculation. Now we're going to, well, that's not true. It's the last concentration formula. We're going to do another calculation, but it's the last formula. Traditionally, molarity is used in science, it's used in chemistry, okay? Most of you are not going to see molarity used in other avenues besides chemistry. However, you may see the term used to a certain extent in nursing, osmolarity, etc. You may see these terms, but we're dealing with molarity, and it's simply the moles of a solute over liters of solution. As you already have figured out, anytime you can have things in moles, what does that allow us to go do with moles? We can do what? What can we get out of moles? We could go mole to mole ratio, yes, if we needed to, but what else can we do? Grams. And then there's all kinds of things you can do with moles. So you can go atoms, molecules, formula units. You can go mole to mole ratio. You can go grams. And so it's useful for science. So real simple, fast question here. What is the molarity of a glucose solution prepared from 108 grams of glucose in 2 liters of solution? And I give you the formula for glucose. If molarity is moles per liter, what do you have to do? You have to get grams to what? Moles. You have to get grams to moles. So tell me how you do that, or do it. You have to tell me how. Go do it. When you get the number of moles of glucose, can you round that number? No, and that's a bummer because you can't. And you get this really long number. Do you get 0.599400599 moles of glucose? And then molarity is that number over what? 2 liters. And you get what for your final answer? 0.30 molar or 0.30 moles per liter. Yes or no? Got it? Okay. I want to mention how I got this because I think somebody's probably wondering. I know we're rusty. Let's just remind ourselves how to do this. This was 6 times 12.01 plus 12 times 1.01 plus 6 times 16. Okay? And this is how I've asked you to round it, is to the nearest hundredth. This gave us the number of moles, then we divided by the 2 liters, and that gives us molarity. What can molarity be used as? a conversion factor. So go to the next page and do those problems. If I were you and I were doing this problem, I would scribble out this capital M and put what there? Mole over liter. Because that's what that means. It means mole over liter. Somewhere on your paper put molarity equals moles over liter. Now, do these using dimensional analysis, not algebra. I want to see dimensional analysis. And there's a reason for that you'll see later. What do I start with? 25 milliliters. What do I convert milliliters to? So 10 to the third milliliters is what? 1 liter. Now what? 2.0 what? Over. Does that make sense? And so milliliters cancel, liters cancel, and there's our moles. What do you get? 0.05, and how many significant digits should you have? 2, so it's 0.050 moles. And properly you should put NaCl. What if I wanted to take this to grams? What would I do then? I wouldn't stop here. Instead, what would I do next? Go to the periodic table, find NaCl mass, and keep going. Do that for the next problem. I will make it easy for you. I'm going to give you the molar mass. The molar mass of aspirin is 180.17 grams per mole. And I'm going to go ahead and give you this one. Sucrose molar mass is 342.34 grams per mole. So do those two. Put proper significant figures on them also. Do you have that set up? Yes or no, guys? Yeah. Good. You're paying attention. That's good. So where's the mistake? Part 1, 2, 3, 4. Good. Right there. That's the mistake. Good job. All right. So 1 liter there. Now, is that right? Good. All right. What's the answer then? 0. What again? 0.45. 0.45 what? Grams. And that's 0.45 grams of what? Aspirin. Actual aspirin, okay? All right, the next problem, 1.25 grams. Now what's next on this problem? What goes on top? 1 mole. What goes on bottom? Grams canceled. 1 liter over 0.25 moles. That's from here, right there. That's what that is. And then 1 liter is 1,000 milliliters, or 10 to the third. How many significant digits? Actually, you just need 2. So it should be what? 15 milliliters. Making sense? All right. The last equation, it's not a concentration equation, it's actually using concentration. And this is diluting solutions equation. That's what this is. This is a diluting solutions equation. Most things you get in a lab type setting, whether that's a medical lab, pharmacy, chemistry lab, biology lab, etc. Most of the solutions that we use come in concentrated form. We dilute them to what we need. This is the equation we use to do that. Very simple equation. What's it remind you of? Remember the gas laws? That's what it reminds you of. And it's basically like that. Concentration of one times the volume of that one equals the concentration of a second one times the volume of the second one. It doesn't matter who you pick to be which side as long as you keep the two things together that go together. So in this problem, we're dealing with a drug and we know that the concentration is 4%. We want to know how many milliliters of the 4%. So if you want to call these 1 or 2, I don't care, but they both are the 1s or they're both the 2s. So if we call them the 1s, let's call this V1 and this will be what? C1, which means this now is what? V2 and this is C2. The other thing I want to point out on diluting solutions with this equation, the great thing about this is it doesn't matter what the concentration unit is as long as it's the same. It doesn't matter what the volume is as long as it's the same. For instance, in this problem it's using concentration in weight volume, but you could do a problem like this if you had molarity. And it would be the molarity of one times the volume of that one, molarity of the second one times the volume of that one. It doesn't matter as long as the units are the same. So to do the problem, C1V1 equals C2V2, and you plug it in. The other thing, don't take it out of percentage. Why not? They're going to cancel. You don't need to take it out of percentage. It's going to cancel anyway. So 4% times V1 equals 0.080% times 250 milliliters. What's V1? What's your answer? 5 what? 5 milliliters. Yes or no? Do we get that? Should you miss this, can you just plug it back in? Yeah, what's 5 times 4? It's the same as 0.08 times 250. All right? So that's the math. Now there'll be more math Monday, but right now this is the math that we're going to do today. So let's keep going and deal with osmosis. When I was in college, I don't remember about this in high school, but I remember in college there was this joke, and we would, like, if we hadn't studied enough for the test, we would say, I'm going to sleep with my book and I'm going to learn it through osmosis. Have you said that?
We're just talking about that.
You were just talking about it. Yep. Well, I'm sorry to tell you it doesn't work, because it would actually be reverse osmosis. Why? Because the book is the concentrated knowledge. Your brain in this situation is the dilute, less concentrated. And how does osmosis work? Low to high. Osmosis actually tries to dilute the more highly concentrated solution. That's how osmosis works. So sleeping with your book will not work through osmosis. Now it might work through reverse osmosis, but it won't work through osmosis. So get the story right if you're going to use that story. So let's write osmosis, then we'll come back to semi-permeable membrane. If you've had a biology, anatomy class, I'm pretty sure you guys are well ahead of me on all this. So you're probably like, this is easy, I know this stuff. So let's talk about it. What is osmosis? Osmosis, I can't talk. What is osmosis? It is the passage of solvent, which is usually water, the passage of solvent, usually water, across a semi-permeable membrane from a solution of low concentration to a solution of high concentration. I want you to make sure that you get this. Osmosis flows from water water in the process of osmosis. Water flows from low to high. Make sure that you get that. Water flows from low to high. The whole goal of osmosis, if osmosis, quote, has a goal, is to dilute the more concentrated side. That's the process that's occurring. Diluting the more concentrated side, and it does that through the use of the ability of the semi-permeable membrane. So what is the semi-permeable membrane? It is a membrane that allows water and small molecules to pass across. But ions and large molecules cannot. A membrane that allows water and small molecules to pass across, but ions and large molecules cannot. I have an experiment for you. It's easy and it's just so cool. And I would not have known about it. I love when my kids do something that I can learn from. It's like double dipping, you know. Your kid learns and you learn too. It's nice. But we homeschool, but the kids go to a co-op on Friday. And in the co-op class, my older daughter's taking a biology class. Well, in the biology class, the teacher sent them home on Friday with 2 bottles and one of the bottles had raisins in it in water. Have any of you done this experiment? Have you done it, Dakota? Have you done it?
Like a long time ago.
Something like this, yeah. This is so cool and so easy. So she came home and she had raisins in one bottle with water. Now I'm pretty sure it's probably not deionized water, but that it doesn't really matter because bottom line, tell me about a raisin. Dried up grape. Is it full of sugar basically? I mean, it's a lot of sugar in there, right? But there's very little water. So would you say that the raisin is the high concentration? And the water is the low concentration. Even if it's tap water, it's still lower concentration and lower osmotic pressure. So she brought this home, and she had to watch it and observe it. So what happened to the raisins in the water? They swelled up. Because what does the solvent water do? It goes from the low concentration to the high concentration. And a raisin is surrounded by a semi-permeable membrane. And so the grape, or the raisins rather, they swelled up. Now, did they look like grapes? They weren't quite as big as grapes, but they really did swell up a lot. So then, the next part of the experiment, the other bottle contained Karo syrup. Now, what's Karo syrup going to be compared to water? High concentration. So she put them in the Karo syrup, and now what are they doing? Shriveling up, because where's the water that's inside the raisin now going? Into the Karo syrup. And so then I tell her, I was like, okay, that is so cool. Now, I want you to put a grape in the Karo syrup. Why do I want to put a grape in the Karo syrup? Because what should happen to that grape in the Karo syrup? The Karo syrup should be more concentrated. I'm pretty sure it will be more concentrated than the grape. So what should happen to the grape? Or what's my hypothesis? It should shrivel. That's my hypothesis. So she's like, oh, okay, I'll do that after I take the raisins out. So, but that is a simple experiment about osmosis, and I hadn't thought of that. Pickles. Do y'all know how to make pickles? What's the whole process of making pickles? Cucumbers in a brine, which might be salt and dillweed and vinegar, or it could be cucumbers in a sugar brine, which is sweet pickles, which is sugar and vinegar and a little salt. But what is the whole process? What's inside the cucumber compared to that solution? Water. So what happens to the cucumber? The water comes out and goes to the brine solution, and brine is a cooking probably more word.
In my 7th grade middle school class, we did the same thing with eggs.
Yes.
So we dissolved the shell with vinegar or something.
Uh-huh.
And then they were just the membrane of an egg. And then we put them in different solutions, like the raisins, and they shrunk and enlarged.
Now, did you boil the egg?
No. They were just jelly.
That is interesting, because I originally told her to do, for a science fair project, I said do that with boiled eggs, but peel the shell off of them. But what you did,
they dissolved.
That makes more sense to do that, because that membrane, I know exactly the membrane you're talking about. Mm-hmm. And that makes more sense to do it that way. And so you were able, did you do Karo syrup and water?
Yeah, it was for the whole class, and we just observed them after.
Yeah.
One of them was in syrup, and then different kinds of water, maybe one had salt.
That is neat. And then we could do it with boiled eggs too. Yeah. That is cool. That's neat. Well, and I never thought about doing it with dissolving the shell. And how long did you have to keep it in the vinegar?
I don't remember, but I just remember.
Do you remember? I would say it would take a little bit for the vinegar to eat that shell up. Yeah.
So if that happens with sugar and salt, if you do the same thing, if you dissolve the shell of an egg and you just have the membrane, you stick it in a water concentrated with food dye, the egg will soak up the food dye. So why doesn't
The egg will soak up the food dye only? It doesn't get, I would think you're adding water to the egg too.
Like the egg pretty much stays the same. It might swell a little bit, but all the color will go inside of it. But there's still some in the water. It doesn't take all of it, but like the water will lighten up and the egg will be really concentrated.
That's a good question. I don't know. I would say it would have to do with the size of the molecule of the food dye compared to the water. I mean, the part of it being the same, I would think they would end up being the same color. The water and the inside of the egg would be the same color, but what you're saying is it actually gets darker.
Yeah, it looks darker inside the egg than it does actually.
Have you ever broken it open and looked at it?
A lot of us.
So you did, so you had like so it really is darker when you opened it up.
Well, I mean, compared to the water,
It looked a lot darker?
it looks darker, yeah. But I'm not sure that it's a significant difference.
What I'm wondering is if it's just a matter of the volume. I don't know. I don't know how to for sure test it, because you got to have the egg completely submerged to see what you're seeing. But then there's less total volume of water in the egg compared to in the cup. So do you see what I'm saying? So it's more dilute in the cup, but I still wouldn't think it would be darker. That's interesting. I've never done that. That's a cool experiment though. That's pretty cool. I'm glad to hear you all doing this stuff. That's good. That's cool. See, I've never done that. I love learning stuff like that. That's cool. When I retire, I'll just be an old crazy chemist doing all kinds of goofy stuff. No, I don't know. That'd be fun though. All right, osmotic pressure. Osmotic pressure is the pressure that prevents the flow of additional solvent into a solution on one side of a semi-permeable membrane. And the key is what I've got bold and underlined. The greater the number of dissolved particles, the greater the osmotic pressure. So let's look at the picture. Now this statement goes with this picture. So I've got it not necessarily laid out the best, but let's look at this picture. So in our beaker, and I realize it's blurry for you guys, but in the beaker we have equal volumes of pure water and then a glucose and water solution. So immediately tell me which one has the greater dissolved solute. Left or right? Right has greater dissolved solute. This is the only one that has anything dissolved in it, guys. So this is going to have the greater dissolved solute. Over time, what happens to the water? It goes into the what side? Through the semi-permeable membrane. It goes into the side with what? That's more concentrated. What is this called? This is called the process of osmosis. This action is the osmotic or the osmosis we've been talking about. The process of going low concentration to high concentration. Which side has the greater osmotic pressure? This side. And this is, because the pressure is greater on this side, it prevents the backwash. It prevents anything from going to this side because the osmotic pressure is greater. That is why the flow goes from low to high. And it always goes low to high. Now then, go down to the next question, and it's a similar question. You'll just draw the picture this time. It says a 0.1 molar glucose solution is separated from a 0.2 molar glucose solution by a semi-permeable membrane. So here is our semi-permeable membrane, and this is 0.1 molar, this is 0.2 molar. And these are my questions. Which solution exerts the greater osmotic pressure? I'm talking about this. Which solution exerts the greater osmotic pressure? The 0.1 molar or the 0.2 molar? 0.2 molar. So 0.2 molar. In which direction will water flow between the two solutions? Now don't say left to right because you might have drawn yours differently. Give me numbers from blank to blank. From the 0.1 molar to the 0.2 molar. From 0.1 molar to the 0.2 molar. And in my picture I can go water direction that way because I have the picture. And I didn't say this, now I should have said it at the beginning. Assume the volume of both of the solutions was the same to start with, okay? So now answer this. Describe the level of the two solutions when equilibrium is reached. Point 2 will be higher and 0.1 will be lower. So 0.1 molar will be lower, the 0.2 molar will be higher. What do you think the concentration will be if equilibrium is reached? What do you think the concentration will be in the end? Point what? Not 0.5, 0.15. 0.15. Because look, one of them is 0.1, one of them is 0.2, so what's half? Or the halfway mark between the two? 0.15 molar. Does that make sense? Assuming there's enough volume in the container and there's enough time passing, etc. That's what you would assume. Make sense or not? There is a question on your sapling about this, and you will see something about this on your test. You're going to be asked to figure these out on your test, okay? All right, the next page starts off with actually a little bit of review and a few new things, just more on solubility. And the first thing is a review, basically, that first sentence. It says, water is the standard polar solvent that solutes are tested in. I think I mentioned this, but let me mention it again. Anytime we as chemists are testing something we don't know what it is, one of the things that often is done is test the solubility in water. Because immediately if we test the solubility in water, does that narrow down the type of compound it would be? Because if it's soluble in water, then that's telling us it's either ionic or it's a small polar molecule. We talked about this. When did we talk about this? When we were talking about what? Polarity, electronegativity. Remember talking about this? Intermolecular forces. And I think you even had a test question. Is water polar or nonpolar? And what did we say? Water's polar, okay? So you've seen that before. We've talked about that before. Like dissolves like. We talked about that. So water's the standard polar solvent. Carbon tetrachloride is the standard nonpolar solvent. So here's the story that could happen. You test it in water, it's insoluble. Then they test it in carbon tetrachloride to see if it's soluble. If it is, then they say it's nonpolar. The intermediate solvent is ethanol. Now that ethanol is the same ethanol that's drinking alcohol. Ethanol is an intermediate solvent. Ethanol is really a cool compound in that it has the ability to dissolve polar substances and nonpolar substances, and that's pretty neat. It's a really neat for that reason. How can it do that? You've actually seen this before, but I'm going to draw it now. This is something you'll be able to draw on your own in a few weeks. But let me show you what ethanol looks like. That's what ethanol looks like. What allows ethanol to dissolve nonpolar substances? What part of that? Say it again. The nonpolar part. What is the nonpolar part of this? Not the OH. The C's and the H's. So this is the nonpolar. That's the nonpolar portion. And this is our polar portion. In fact, there was a special name that we called that OH. What does that OH bond allow it to do in water? OH, NH, FH, hydrogen bonding. Hydrogen bonding. So the reason ethanol dissolves in water is because it can hydrogen bond in water. The reason ethanol will dissolve oils is because of this carbon-carbon bonding with hydrogen, which is the nonpolar portion, which makes ethanol extremely useful in the food industry and in the medical industry. Essential oils. Now, I personally don't use essential oils, but I'm imagining some of you may know, at least know about them. They are dissolved in ethanol. Why? Because they're oils. Will they dissolve in ethanol? Yes. Will ethanol then dissolve in your body? Medicines that are nonpolar, what do you think they put them in to be the carrier to get them into your body? What's your body mainly made up of? Water. So you need things that are soluble in water, right? If it's going to go certain places in your body. Those certain places meaning the places that are filled with water. So if it needs to go to the water areas of your body, which is the majority of your body, we hope, then how is that going to get there? It has to be in something that can carry it in water. Guys, what happens when you try to put fat in water? It doesn't mix, does it? It doesn't mix. Now, are there certain things that are fat soluble? Sure there are. Vitamin K, vitamin A, vitamin D, vitamin E, all of those are fat soluble vitamins. Do we need those? Yes, that's actually the last lecture of the semester is going to be about those. And we need those. And they're fat soluble. So anywhere you have fat, you've got those stored somewhere dissolved in your fat. But the rest of the vitamins we need are all water soluble. And so there has to be a way to get those nonpolar substances in a polar way, and that's with ethanol. That's what it is used for in the medicine world. That's what I'm telling you. One of the most common medicines that contains ethanol. Most of you have had it before. Anybody know what it is? Some of you look like you're taking it tonight.
NyQuil.
Thank you. What's NyQuil do? Helps you sleep. Why does it help you sleep? Main reason is because it's a lot of ethanol. Most of the time when you're sick, you need to just sleep. But what's the other reason for putting that in there? Because does it dissolve the nonpolar medicine? Yes. That's what dissolves it. Guys, the amoxicillin, remember we talked about have we talked about amoxicillin? Yeah, we talked about the shaking it up. It's obvious it's not water soluble. Why is it obvious it's not water soluble? Because it's a suspension, it separates in water, right? If it's not water soluble, chances are it's what? Nonpolar. Now, some of you may be saying, well, why don't they put it in alcohol? Well, typically you're giving that to kids and we don't want to kill the kid, okay? But chances are, would it be soluble in ethanol? It probably would be. It probably would be soluble in ethanol. Now, a question that I just am having in my brain right now is why don't they put it in a little ethanol, dissolve it, then put it in water and dilute it? I don't know.
You might have just answered this with what you said, but so how do they make Dayquil that's non-drug?
The drug, I don't know what drug it is. It could be the drug's water soluble. It could be that it gets where it's going with, and it could be that there's a little bit of alcohol. I don't know. Aren't those Dayquil, aren't they liquid gel tabs? I don't know. I don't take that. I don't know. But there's also other cold medicines that are in tablet format. But what you could do, you could actually, again, sit down and crush up, Sudafed pills, or not necessarily Sudafed pills, but any cold medicine. Crush it up and see if it dissolves in water. And I would bet majority of them do not. Some of them will, but some of them won't. And so then you could find out, that would be one reason they're using that in ethanol. So, and again, I don't know. I've not tried this. Okay? Maybe I need to create a list of, my bucket list of to-do experiments. I don't know. I doubt if I'll do those, but I think of them and then I forget about it tomorrow. Your flavorings, vanilla flavoring, what's it in? Not what food, y'all are hungry. Not what food, what's it in? What is the vanilla bean dissolved in? Ethanol. Ethanol.
Okay, so ethanol, you just said is the alcohol. So it's all dissolved in ethanol. It's all dissolved in alcohol?
Well, when you say it's all, what do you mean?
Well, like you're saying, like dissolve, like the medication has.
Some medications are dissolved in ethanol, which is drinking alcohol, to get them where they're going. Not all of them are, though. That's what I'm saying. Some of the pills we take, chances are they are not water soluble. But it could be that when the stomach acid hits them, that's powerful enough to react them without them being water soluble. So there's other chemistry going on besides just dissolving. But some things are dissolved in water to help them be absorbed maybe more quickly. And alcohol is processed very quickly in your body. Okay? Does that answer kind of what you were asking? Maybe? Okay. All right. The next little part here that says other interesting information. When I put this in to start with, I will just be very honest with you, I was on a soapbox. That's why it's here. Just bottom line. It's here because it was one of those things I went from, I'm talking about ethanol, I'm talking about the intermediate solvent, and then I'm just starting researching, and I'm like, this is really interesting, I'm just going to throw this in the notes. Now, is it only there because I was on a soapbox and it was interesting? Not exactly the only reason. Let me tell you what is here that's pertinent to what we've been studying tonight. Can anybody tell me before I tell you? You're seeing it. What is it? Do you see the volume percent, the blood alcohol content? It's listed in a percentage that we talked about tonight. Volume percent. And is gram per liter, could that also be what would be considered maybe it could be converted to molarity easily. It is a form of concentration. So this does relate. Now, that wasn't my first time I taught it, what I spent the time talking about, and I will tell you we will come back to this when we get into ethanol, how it works in your body. We will get into that. But for now, let's talk about just a little bit of how these numbers could be used. And this is kind of interesting when you think about it. What is the legal limit for DUIs? 0.08? Okay, that's what I was thinking. Okay, so 0.05% is the euphoria, talkativeness, relaxation, and then 0.08% is the legal limit to be considered drunk, driving under the influence. And so not much, guys. I mean, it doesn't take much to get you there. What does that mean? So let's say if it is 0.08%, what does that mean? 0.08? No, it's volume because it's ethanol. So 0.08 milliliters in every 100 milliliters of blood. That's what that means. Okay? So 0.08 milliliters of ethanol in every 100 milliliters of blood. Guys, that is not much. But it already, I mean, I've never done those glasses where it makes you feel like you're walking drunk. But I've just read about it. But have you done them? Some of you have done them and it just totally, or maybe you've been drunk, maybe you know. But you know what that feels like. I mean, you can't walk in a straight line. With 0.08, that's not much. That is not much at all. So if your body, I could give you a problem. The average person has 5.5 liters of blood. How many milliliters of alcohol is there? You don't have to solve it right now, but you can later write it down. If you have 5.5 liters of blood in your body, now they got grossed out this morning. I told them they had almost 3 2-liter Coke bottles full of blood in their body. I'm like, oh! But isn't that cool? I think that's pretty cool when you think about it. I mean, think about that. You've got almost 3 2-liter Coke bottles full of blood in your body. I think I probably do, because I'm bigger. But, I mean, isn't that neat? That's neat to think that. And so if you had a blood alcohol concentration of 0.08%, you can do the math to see how much total ethanol is in your blood. You could do that math to figure that out. You could even then go, there's all kinds of things you could do with that. Okay? That's the kind of thing, I just think that's interesting. All right? And we're going to get back here later. I've already preached a sermon once tonight. I won't do another one. But if you are drinking, be careful. Okay? I don't choose to drink. I've seen too many things of what it does. All right, osmosis. 3 words that we want to look at. And I'm going to tell you what one of them means in general rule of thumb words, and then I want you to tell me what the other 2 mean, and then we'll write the actual definitions. If I say to you an isotonic solution is like body fluid, it's the same osmotic pressure as body fluid, then what would a hypotonic be? Lower, and what would hyper be? Okay, you got it then. All right, so isotonic, and there's actually 2 ways of looking at it. One is with body fluids, but another is just looking at comparing 2 solutions. So when we say we have isotonic solution, what we're meaning is 2 solutions with the same osmotic pressure are said to be isotonic. 2 solutions with the same osmotic pressure are said to be isotonic. We can also say that an isotonic solution has the same osmotic pressure as body fluids. Isotonic solution has the same osmotic pressure as body fluids. Examples of isotonic solutions are 5% glucose and 0.92% saline or sodium chloride. Those are isotonic solutions. Both of those are isotonic solutions. Hypotonic solution, we say, has lower osmotic pressure than body fluids. And hypertonic is higher osmotic pressure than body fluids. I've already told you the answer to what I'm going to ask next, but see if you can fill it in, remembering our raisins. Cells placed in hypotonic solutions, and then I'm going to say the same thing, cells placed in hypertonic solutions What do cells do when they are placed in hypotonic solutions? Think about that. Think about the raisin. The raisin's the cell. You put it in hypotonic like water, what's it going to do? The water's going to go into the cell. So it's going to do what? Swell. It's going to swell. Cells placed in hypertonic solutions, what? Shrink. And then two more words we're going to talk about before we get to the actual, we're going to go to the middle of the page again before we go to the top. But there's two more words that deal with this that you probably have heard about from your anatomy class. What are those two words? Hemolysis and crenation. Hemolysis is the swelling or rupturing of red blood cells due to solvent flowing into the cell from a hypotonic solution. The swelling or rupturing of red blood cells due to solvent flowing into the cell from a hypotonic solution. Crenation is the what? The shrinking, or you may call shriveling, same thing. The shrinking or shriveling of red blood cells due to solvent flowing out of the cell into a hypertonic solution. I don't know that I've said this, but I used it here. SOL'(N) means solution. That's just a little shortcut. SOL'(N) means solution. Above this, this actually came from, and you can see I put the source at the top of it. My first semester teaching Chemistry 109, I was very fortunate, I felt like, to have a student in the class who actually worked in the hospital on the urology floor. And I guess she was a CNA, I don't know for sure what she was, but regardless, she taught me a lot about this topic because I knew nothing about this. And just like I told you all the other night when I showed you the IV bag, I knew nothing about stuff like that, or I may have not told you that, but it was really interesting to me what she taught me from that semester. She gave this to me and she said, you know, I found this, and she said, these are things that we use all the time. If you are in the field working in some capacity, which I know some of you are, this is familiar to you. The rest of you that are going to be nurses, you will see this. I'm not going to teach you this. This is not what I'm here to teach you. This is a nursing class. What I want us to do, though, is look at this because it's pretty interesting for a couple reasons. First of all, the thing I noticed when I first saw this was dextrose. And I'm like, what's dextrose? Does anybody know? It's a sugar. Which one is it? What's the other word for dextrose? Say it. It's not sucrose. It's actually glucose. Dextrose and glucose are the same thing. So the first thing I did was, why can't they just call it glucose? That stuff drives me batty. And I know you all feel the same way about chemistry. Why can't they just call, you know? But that was like, why do they call it dextrose? I don't know. It's glucose and dextrose are the same thing. They call it, though, they don't even call it dextrose. They call it D5W. What's D5W? Do some of you know this? Some of you heard this? No? Well, the D5W means dextrose at 5% in water, and that's an isotonic solution. Saline, which they call normal saline, is the 0.9 or 0.92% sodium chloride in water. It's isotonic. And then the lactated ringer solution that I showed you Monday, or whenever I did, last Wednesday, that is an isotonic solution. Most of the time, if you're having just something general done, you're going to be given the lactated ringers. Depending on what else is going on with your body, you might be given the saline, you might be given the dextrose. When for sure would you be given a dextrose solution? Or when would a patient receive dextrose? What do you think? If they had low blood sugar. Possibly any scenario where there was low blood sugar and there was a need for extra energy. Glucose is the energy for who in your body? What organ uses glucose? The brain. So if you need better brain activity, you're going to maybe need some glucose. So all of you are saying, let me just go get some sugar right now, right? No. The glucose is different than the sucrose. It's similar. What interested me when I read this, and everything here is original except for this why. That's mine. I put the why. Everything else was from the paper she gave me. And what interested me is I can understand why you would use isotonic solutions in dehydration. I could understand that. I could also definitely understand why you would use a hypotonic solution in dehydration. That made perfect sense to me because you want to really add the water to the cells. Do you understand that? That makes sense to me. Then I get down here and I'm reading all this, and half of it I don't know what we're even talking about. But then I get down here and I understand a dextrose 10%, which is hypertonic. Definitely when nutrition with glucose is required, that totally makes sense to me because that is some major glucose. But then it said water replacement. And I'm like, okay, I had my brain on up to that point, and then why? Because in our knowledge, what does a hypertonic solution do to cells? It pulls the water out of the cell, right? into the hypertonic solution. So why would you say you do this for water replacement? And I asked that question. And the answer, I asked a doctor friend of mine, and the answer was this. One of the main times that that's used is in burns. Tell me, even just sunburn, I'm not saying they use this in sunburns, but what happens when you have a burn, a severe, fairly severe burn? Blisters. Meaning, so let's just say you have a burn, whatever caused it, I'm not going to go into, but let's just say you have a burn on your arm. What's your arm going to do? Blister. Meaning it gets wet, right? Underneath the cell, underneath the skin, the very first surface of the skin, it's just a lot of fluid is here, right? In general though, what's a burn? Any burn is dehydration. So if it got burned, how did it get wet? Where did this moisture come from? Your body. So what happened is the fluid, the liquid, has moved out of the cells onto the surface. Does that make sense? So are the cells beneath this dehydrated? Yes. And so the purpose of the hypertonic solution was actually to cause this moisture, this water, to go back where it belonged. Does that make sense? So they gave this solution to pull the water away from the areas that weren't supposed to have it into the places that were. That was the best explanation that I can give, that I understood. Does that make sense somewhat to you all? And again, there are all kinds of things I'm not going into. There's that fluid shift. I've heard all these words and I'm just like, okay, I'm not following you. So I just kind of zone out there like you all are. Go on down though, let's finish up dialysis and then we'll be done for the day. While I'm talking about dialysis, I'm going to be passing something around for you to look at, feel of, whatever, and I'll talk about them. I'm going to talk about what dialysis is, but real quickly I'm just going to tell you what this is and then I'll let you feel of it and look at it. This is a cartridge from a peritoneal dialysis machine, okay? Notice this. I want you to feel of this, okay? So notice that, pass it around, and we'll talk about that in just a minute, but let's talk about regular dialysis first, okay? The kidneys typically clean your blood. That's the purpose of the kidneys, is to clean your blood. But when the kidneys don't work properly, dialysis has to be done, and it's called, what is actually the name is hemodialysis, is what's usually done. There are actually two different forms of dialysis that I'm aware of. One is the hemodialysis, which is this machine that you've got on the next page. This is hemodialysis. This is a hemodialysis machine. And the process of how this works, in general, the process of how this works is you will have the blood coming out of your arm into this machine, and this machine has tubing, and what's this tubing made out of? In general. A what? What is it? What does it act as? I'm not asking my question right to get the answer I'm looking for. But how does it work as a filter? What is the body's, every cell has as its filter in essence? A semi-permeable membrane. So what is all this tubing? A semi-permeable membrane. So all of this tubing, now what you're holding in your hand that's passing around is not this machine. It's similar though. There's parts of it that are similar. The tubing there, though, is not semi-permeable. So here's what, let me go backwards. So what's going on? You've got the blood coming out of your arm, the dirty blood, goes through the machine. What is inside the machine that the tubes are passing through is what they call here simply the dialysis fluid. But what is it? It is an isotonic solution. And all of this, I'm just basically going to read what I wrote up here. Treatment takes several hours. A patient's blood flows through a long tube connected to a cellophane membrane. That's the semi-permeable membrane that is suspended in an isotonic solution that contains sodium chloride, potassium chloride, sodium bicarbonate, and glucose. That's what's in here. Small molecules like urea cross the membrane into the solution, meaning coming out of the blood, cleaning the blood of that. But red blood cells and other larger molecules don't come out. They're left in the blood. So the whole purpose of this is to act as the kidneys do when the kidneys are not working properly. That's how this is working. So they work as the kidneys work when the kidneys are not working properly. The peritoneal dialysis. First of all, let me ask this question. Does anybody know anybody that has dialysis or has had? Tell me what you know about it. Say it again. Tiring. That's what everybody tells me. It's very tiring. It's very, very tiring. And that, the first time somebody said that, I'm like, but why? Your blood's cleaner. It ought to be exhilarating. I mean, it seems like to me it would be, but everybody says it's tiring. They say it absolutely wipes the person out. And I mean, other than the fact that obviously your blood's like coming out and going in, that would be tiring.
I didn't know you're not supposed to drive afterwards, and my uncle died right after his dialysis treatment on his way home. So
Are you serious? Wow.
just got finished, and he was supposed to have a ride, but he didn't have one, so he drove home, and he crashed, because like you said.
It just literally wiped him out. Wow. And so it's something that your body is not supposed to have your blood coming out of it, basically. And that's one of the things that really affects, I'm assuming, that really causes the person to be wiped out. I mean, it's just really hard. The peritoneal dialysis is supposed to be not as hard on people. And this, what you're passing around, the way this works, first of all, does anybody know about peritoneal dialysis? Does anybody know about it at all? Can anybody tell me anything about it? I want you to be the expert if you know about it, because I'm not. Nobody knows? So this is how it was explained to me. First of all, a student explained it to me, that first student that I had, then somebody else maybe a year ago gave me this. This is from the machine that cartridge that you're holding, the rectangle cartridge, that is a semi-permeable membrane surrounding that, but your body also acts as part of the filter as well. So the way this thing worked was that cartridge goes in a machine, there's fluid in the machine, and you can see those ports are all labeled, those tubes, but I'm not going to go through that because I don't even understand it at all. But the gist of peritoneal dialysis, of how it works, is your peritoneum cavity or peritoneal cavity, and you guys, again, I've never had an anatomy class, so I'm probably way off here, but am I close? Okay. So the peritoneal cavity is full of stuff. Yes? Is it full of a lot of surface area of cells? Yes? I'm thinking intestines, stomach, organs. Are we with me here? Okay. All of that stuff has a semi-permeable membrane, yes? So here's how the basics of peritoneal dialysis work. And I'm not going to deal with the hookup. I'm just saying the basics. And I'm one of those people, if you ask me which direction to go, I have to turn around. So bear with me here. Here's what's going on. The person is lying down. There is a port, whatever you want to call it, shunt, hole, however you want to say it, in their peritoneal cavity. Isotonic fluid, dialysis fluid, gravity flows or pumps into the peritoneal cavity. Patient is lying down. What is all of this? huge semi-permeable membrane area, yes? Yes? What's the flow? Well, it's isotonic, right? This is isotonic that we're putting in, so what is going to be the flow? Bad stuff out into isotonic solution, yes? Then, after however many hours, this is actually done many times when patient is sleeping. After several hours, turn patient over on their side or other side, whatever, drain it out through gravity flow, and it looks like urine. And it is easier on the person. So instead of taking your blood out of your body, what are you doing? You're letting your body do the filtering for you. That's the gist of it. Have any of you've not ever heard of that either? I had never heard of it before. Have any of you ever heard of it? No? In my 8 o'clock class, and this is who I've heard it's used for, is children, but I've also heard now it's also used for adults. But in my 8 o'clock class, a friend, or a student rather, had a 3-year-old cousin who did this when she was little. I think now she's okay, but she did this. So that is where we're going to stop for this. Now, before you put all your stuff up, listen to me real quickly, because you got to stop, okay? I should never tell you before we put our stuff up, because you immediately start doing it. Here's what you have to bring with you on Monday. There are, which you have them because you're looking at them right now, these notes. These notes end with a page that looks something like this, okay? But that's not all you need, so pay attention. That is the ending of these notes. Then you also have another set of notes. I'm looking up here to see if anybody's got them handy. Then you also have another set of notes that have another pH scale on them, and mine this time is not in color, but this is what it starts with. And there's more math in this section again. So print out, and these say day 19 and 20. So print those out, and you have under, I think it's practice, extra practice homework maybe, or something like that, practice homework. You've got practice problems for test 4. Print those out. Have all of that printed for Monday, okay? And then be ready to go on Monday. And I will see you then.